Hello and welcome to video 7.8. Thermo continued. This time we're going to talk about refrigerators, AC, and something called COP. I am sure that there have been lots of times that you've been sitting around your house wondering, how the heck does my refrigerator actually work? And how does my AC actually cool down a room? Well, that's what we're going to talk about today. These appliances, refrigerators, air conditioners, and heat pumps can be thought of as heat engines operating in reverse. Because remember, for the heat engine, we have heat flowing from a higher temperature down to our lower temperature reserve, with some allowing us to use it for work of some sort. And this is how it naturally occurs. So this is our heat engine here. But now, essentially, as I said, rather than doing that, we're going to look at the heat in this picture. And here, the heat is flowing from the cold to the hot. So it's flowing from our low temperature reservoir to our higher temperature reservoir. The important thing to remember is that it's flowing there by force, not spontaneously. So now in this particular case, by doing work, heat is extracted from the cold reservoir and exhausted to the hot reservoir. So we have to add in work on our system, and then we can pull some heat energy out of our colder system. So let's take a look at this picture here of a refrigerator. This is a little bit older one in that these coils are visible on the back, but typically we have inside modern refrigerators, we have the coils on the back here, shown in yellow here, and they are scrunched down together near the bottom of the refrigerator. But on this particular fridge, they're spread out all around the top, and they also have these fins here, just like we were talking about the other day in class, where you have fins to allow heat to be dissipated more quickly around motors and engines and things like that. So what we have and how this works is down here at the bottom, we have our energy source, where our work is going to come from, and it's a pump or compressor. And what happens is that there's a gas in here that is compressed. And the gas that gets compressed is a high pressure vapor, and that gets pushed into these coils on the back. The high pressure vapor has a lot of heat in it, has a lot of energy in it, internal energy in it, because it's been compressed so the temperature goes up. So through the transfer of the compressed gas in these coils, it allows the heat to dissipate flow out through to the outside. So we're losing some hot energy there. Now the condensed coils on the outside of the fridge or near the bottom are in high pressure. By the time the gas gets to the top of the coils, it has lost a considerable amount of temperature because it's been losing it through the fins and radiating and conduction and convection out the back of the refrigerator to the environment. So now the gas gets to the top near this expansion valve, and when that valve is open, the gas is allowed to quickly go inside. It's already at a colder temperature than it was down at the bottom, and because it's now allowed to expand, it's going to cool even more. Now these cooling coils are inside of your refrigerator. And with these being colder, these temperatures here are less than room temperature, and they are less than the temperature of the fridge, which means that we can take more heat energy from the inside of the fridge and pull it to here, so the heat from the inside now goes to these cooling coils. and absorbs more of that heat energy, and then the gas is eventually sent back here to the compressor where the process starts all over again. So we compress gas, make it hot. We allow it to go through these coils, which allows it to dissipate the heat to the environment. That's our QH, our Q hot. We then allow it to expand, get even colder, and it absorbs QL, an amount of energy from the inside of the refrigerator, and then that process keeps repeating over and over again. Now notice that the amount of energy that we put in as work, most of it goes to the heat that leaves the coils on the back. Whereas we get a little bit more coming from inside the fridge. So we're cooling it some, but not nearly as much as what's being cooled with the coils on the back. Which is why really you cannot cool your room opening your refrigerator door, because your QL is so much smaller than your QH is that essentially every time your refrigerator's compressor goes on, which it does periodically, you are heating up the house, you're heating up your kitchen. So even if you do open the door, you're not going to cool your kitchen very much, because your fridge is going to have to turn back on again and compress some more gases, and then you're going to increase the temperature again anyways. This is also essentially how an AC works. The only difference is because the point of an air conditioner is to cool down the internal environment of the room rather than heat it up like the refrigerator does. The portion of the air conditioner that has these coils in it, here, the high pressure coils, must be outside. It has to be outside of the building, outside of the room, so that the hot air can dissipate into the external environment of your house rather than staying inside your house. So if we take a look at some equations that go along with this, we're going to start with the same equation that we've been talking about before for heat engines. QH equals W plus QL. This is again the conservation of energy equation. We're not going to break conservation of energy. The difference is that now that we're going in the opposite direction, that all the arrows are in the opposite direction, technically these all should be negatives because they're opposite of what they were before. However, with them all being negatives, they still all cancel out with each other, so it's the same thing as if we wrote them as positives. But I just want to make sure you understood that they are actually all negatives. So now, when we think about refrigerators and ACs, if we continue our comparison with heat engines, the next thing we talked about with heat engines was the efficiency. And remember, we said the efficiency was our benefit over our cost. And for a heat engine, it was the work that we got out over the amount of energy we got at the hot temperature. So benefit over cost. And because we knew that we could never get more work out than the heat we have, it always had to be less than 1. This is not actually true here in an AC or a refrigerator, because how much heat we can get rid of into the cold region, or is related to, is now going to be related to the energy we use to plug in the appliance, which is here. Here. So our W is the energy from plugging it in, and the QL is the heat we get rid of from inside. So again, if we use the QH equals W plus QL up here, we can rearrange this COP equation to end up with QL over QH minus QL. And now we have an issue because here this can be greater than 1. If we are able to get rid of a lot of heat energy from the inside of our refrigerator or the inside of our room, then we can end up with a number greater than 1, which means that we can't use the same terminology as efficiency, because remember, 100% efficient means that it's 1, or has to be that it's at 1. And so ideally we could have a 100% efficient engine, but reality says we can't, so our numbers always have to be less than 1 when we're talking about efficiency. So instead we talk about this thing called COP. COP stands for coefficient of performance. And that is still the same idea. It's still the ratio of the benefit over the cost of the refrigerator or the AC, but now it can be a number larger than 1. Now our ideal COP is where our heat we get rid of over the work we put in is actually about our temperatures rather than the heat flow. So COP ideal is the temperature of the low reservoir over the difference between the temperatures in the two reservoirs. And again, that's the ideal, but we often can't ever get there. Let's start with it. Let's look at an example here of what we would do with this information. We have an ideal freezer that operates with a COP of 7.0 in a 24 degrees Celsius room. I want to know what is the temperature inside the freezer. So I know that this has something to do with COP. COP is 7.0. I know that the high temperature is 24 degrees Celsius, but I need this to be in Kelvin. So 24 plus 273 or 297 Kelvin. I want to know what is my low temperature, and because this is ideal, I know I can use the equation that COP is equal to TL over TH minus TL. Alright, so let me put the numbers in. We have 7.0 equals TL over 297 minus TL. Multiply both sides by the denominator, and we get that 7 times 297 minus 7 times TL is equal to TL. So 8 TL is equal to 7 times 297. And yeah, I dropped the 0 for the moment, but it'll come back in my final answer. So TL turns out to be 259.9 Kelvin, which is great. Alright, that's the temperature it is in Kelvin, but when we're talking about a freezer, we really want to know what does that actually mean in terms of Celsius, and that is approximately negative 13.1 degrees Celsius. So, and again, we can use this version of the COP equation because it is an ideal freezer. Otherwise, we would have to know the size of the freezer, and we'd have to use the equation with the Q's in it. Most of the time, we won't need to worry about that, though, because we will be looking at the ideal. Bye for now.